All right, what's up, everybody? Time for some bell curve action. What we're going to do today, little stats for you, but I think this overlaps with some AP Psych ideas. I've seen a couple sample questions on the SATs related to the normal distribution, this kind of fundamental understanding of the bell curve. So anyways, let's jump in here. So this is our question. Pause the video, check that out. So we've got IQs are normally distributed. Got the mean, standard deviation. We want to find what percent of people have an IQ below 130, above 115, and between 85 and 130. So we know from last class from the empirical rule, right? We know for any distribution that's normal, that's unimodal and roughly symmetric, by definition, the empirical rule, about 68% of data is within one standard deviation, about 95% of data values are within two standard deviations, and about 99.7% of data values are within three standard deviations. So we're going to kind of build off that idea a bit. So for us here, first thing I'm going to do is draw a picture, right? Anytime we're doing a normal model question, first thing we want to do is draw a picture. So we know for our IQs here, we know we've got a normal model with a mean of 100 and a standard deviation of 15, right? So this notation, this just means normal. That's the mean, mean, and then that's the standard deviation. And so this is mu and sigma. We'll worry about what those aren't at X bar and SX in a future unit. That deals with the difference between a statistic and a parameter. So if I want to label some IQs down here, we know the mean is 100. And then, right, add one standard deviation takes us to 115. Add another standard deviation, 130. Add another standard deviation, 145. Right? So just adding 15 each time. And of course, on the left side, we're just going to subtract 15 each time. So we're going to have, what would I start over there? We're going to have 85, 70, and 55. All right, so that's our first thing. Now, combining that with the empirical rule, we know, right, about 68% of people are going to have an IQ between 85 and 115, right? That's what this is telling us here in red, right? So, sorry. So about 68% of people are going to have an IQ between 85 and 115. About 95% of people are going to have an IQ between 70 and 130. And about 99.7% of people are going to have an IQ between 130 and 145. Right, so that's all good, but that doesn't really help us answer our question, like what percent of people have an IQ over, say, 130, I think was part A. So in order for us to answer that, right, we got to do some math. We know, for instance, 95% of IQs are between 70 and 130. So I bet you could pause the video right now and figure out what percent is just in this section. But beyond that, right, if we're going to look at questions we want to look at between maybe 85 and 130 or something, right, we're going to want to figure out what percent of data value, right, fall in each of these individual sections. And that's your challenge right now. Pause the video, right, and see if you can use what we know about the empirical rule, 68, 95, 99.7 rule, to figure out, right, the value of each of these question marks. Of course, they should add up to 100%. Right, so check your work, see how you do. So let's do it. Now that you have unpaused, what is going on here? So anyway, sorry. We know 68% of the data values fall within here. Right? Sorry about that. So of course, I'm pretty confident that everybody in here figured out that these are each going to be 34%. Now think to yourself, why can we just divide by 2? What property of this normal distribution tells us or allows us to divide by 2 and know that these have to be the same size? What's that? It's symmetric. That's right. So since it's symmetric, right, these have to be the same size. Now for our second piece here, a common mistake I see. Now that's not a bad thing, right? If I say a common mistake, that means like a lot of people do it. That means it's probably a good idea. But a common thing we see here is a lot of people, 2 different ideas. Some people want to just take 95% and divide it by 4. But that would be considering all of these the same size, right? And we can't do that because this orange section is definitely smaller, right, than what's in red here, right? That has to do with the nature of the shape, right, of the curve here, right? So this orange section is smaller than the red one, and then this brownish one is smaller than orange, and so on. Right, so we can't do that. What we can figure out, right, we know this interval contains 68%. And hopefully you figured all this stuff out on your own first. If not, definitely pause it right now and try to finish this off. We only want to figure out, right, what's this and what's this. Well, we know the entire orange section is 95%. So if we then take away that red section and that red 68% in the middle, right, that'll just leave us with the outsides, that 27%, right? So we're starting with this 95, which is this whole orange section. We're literally taking away this middle 68%. So we're just left with these outsides. And of course, since the curve's symmetric, we then divide by 2. And so then we figure out, why did I end up doing it in blue, that these sections contain about 13.5% of our data. I bet you could finish it off from here. Right, so similarly now, we know 99.7%, I guess I'll write on the top. We know 99.7% is along this whole green line. We also know, what did I use? I guess orange. We also know from here to here, roughly, right, that middle 2 standard deviations contains 95% of the data. So of course, you guessed it, we're going to take, I don't know, we'll go with purple again. 99.7, we're going to, what am I doing? We're going to subtract in orange this 95 here, and that's going to leave us with 4.7%, right, for this and this chunk, also known as this and this. But then, right, we divide by 2. And so we're going to get that these, why did I mess up my colors? Are each 2.35% of the data. Lastly, if 99.7% of the data is between 3 standard deviations, that leaves 0.3% for these outsides. Whoa. And of course, divide by 2. I've said, of course, a lot, right? So this is 0.15% of the data. And that's why when you look at this, that's why there's like barely any space in there, right? You can barely see anything under there, right? That's because it's almost nothing. It's 0.15% of the entire curve. And then, right, this curve, just on a side note, this is like an asymptote, right? This theoretically extends infinitely in either direction. It gets closer and closer and closer to the axis. So there we go. Now we got a bell curve with a more detailed labeling of the variable. All right. Boom. Now what? What do I want to do? I want to stop annotating. All right, so let's answer these. So what percent of people have an IQ below 130? Now this is no big deal. There's just a much neater version of the picture we just figured out. So we got 100 right here, 115 right here, 130 right here. We want below 130. There we go. Now, one cool thing I like about these problems, there's a lot of different ways to do them. So like, sure, you could just right off the bat, add all of these percentages to the left of 130, right? Plus all those. I'm not going to rewrite all that because it'll take forever. Or like, what are some other ways you could do it? Maybe you do 100 minus 2.35 and 0.15, right, to get our 97.5%, which of course, if we wrote it in its decimal form, we got to be aware would be, what am I doing? Would be 0.975. So we can subtract, we could add all these in the circle. That would give us the same answer. What's like another approach that you could take? Ooh, here's an idea. From 130 down to here would be 95% of the data. Oops, 95. All right, never mind. My pad definitely does not want me to do that. But that pink section would be 95, right? And then we could add this 2.5% here, right? So one thing I like, there's a lot of different ways to do these, right? You do what works for you. Moving on, 2 more, we're done. I should not use PowerPoint anymore because it's weird with the annotating. It's not what I'm used to. I got to go back to what I know. So level 115, right? Same idea. You guys can probably just figure this out. You don't need me for this, but really quick, we'll just keep it with the pink here. So 115 was right here, right? This was 100. So now we just add all those, right? We can add those 3%, and we can get 16% if we add all these. Or maybe we know that from here to here is 50, and from here to here is 34. So maybe we just subtract both of those from 100 to get 16%, right? And then, right, there's all sorts of other stuff you could do. Maybe on the right side here, we know from here to the right is 50, and then we just take off this 34%. 50 minus 34 works, right? Be creative. See how many ways you can figure out to get that 16%. One thing, right, I want to point out, right, course, this is all about the picture. So it's all about drawing the picture first and labeling. Once we do that, it's pretty simple. And last but not least, between 85 and 130. So 85 was right here, right? 100, 115, 130. So the boring way is we just add these four percentages. I'm sorry, we don't add that one, right? We don't add that because we want between here. Or maybe we already know that's 68 plus 13.5 to get our 81.5%. Or maybe we try something, I don't know, different. Maybe, I don't know. Nothing's jumping out at me as like clearly much easier, right? I could subtract all these outside things from 100. But 68 plus 13.5 probably going to be your most efficient step, right? Which is, of course, the same as adding all these. All right? Be creative. Try to think about it. So that's it. That's why I work with the empirical rule. One last comment, especially if you missed this from class. So we can use what we know about the empirical rule to kind of define outliers in a different way. So we have two options to determine outliers. One is we already know we can calculate the fences. We saw that idea with the box plot, right? And that's going to work for any data set. So this works for any data set, no matter the shape, right? It could be bimodal, whatever, skewed, doesn't matter. But specific to the normal model, right? So this only works for the normal model. Here, now we can say that if a data value is more than 2 or 3 standard deviations from the mean, it's an outlier. Now the 2 or 3, I mean, some textbooks say 2, some say 3. But if we think about it, who cares what the definition is in a book? Let's understand it, right? It should make sense to say, all right, about 95% of the data, right, is within 2 standard deviations. So only 5% of the data is outside 2 standard deviations from the mean. That's pretty unusual. Sure, that's weird. Maybe that's an outlier. Right, or maybe if you have a more strict definition, some books will say outside 3, because, right, of course, 99.7% of data values are within 3 standard deviations. So if you're now outside of that, right, only 0.3% of data values are outside 3 standard deviations from the mean, right? So that's pretty unusual. The AP exam is going to accept either definition. I know math people, that's like really bugging out that I'm not just giving you an exact answer, but welcome to stats. So I think that's it. Next video, we'll start to look at what happens if I say what's the probability someone's IQ is above 117 and it doesn't fall right on one of those exact 1, 2, 3 standard deviations away. Until then, enjoy the rain.